This talk is memory talk. It devoted to the Igor Borisovich Simonenko. I am not a student of Igor Borisovich, direct student, but influence of his results on my investigative weren't very essential. And one of them is so-called factorization in the in LP space. So LP factorization was introduced by Igor Borisovich in 60s, initial 60s. It was very essential step of the development of the theory of Riemann-Gilbert problem. It was the passage from the girders and continuous symbol to the symbol with the general symbol of space L infinity. So you introduce some notation. Entonces, T is unit circle, LP of T, P space, usual SP space, S is usual Cauchy singular operator, P plus minus is analytic projectors, LP plus and LP minus is the image of the analytical projector. It's the function who analytic correspondingly inside and outside of unit circle. We mentioned that LP plus coincide with the famous Hardy space correspondingly inside and outside of unit circle. Okay, so we consider the function A. Is function A as the symbol of so-called Toeplitz apparatus. Toeplitz apparatus is apparatus P plus A P plus, that acting in LP space with plus. Notation of LP factorization, P factorization. So the function, essential bounding function A of T admit LP factorization if we have a representation of this type, where factors A plus, A minus belong the correspondingly LP analytic space with index P or index Q, where Q is conjugative number. Furthermore, we have the condition B. Condition B is the bounding of this projector, in space LP. Its notation was introduced by Simonenko. It was the generalization of corresponding notation on the space L2, and the space L2 results in L2 that was obtained in the Devinats or Weidam in initial 60s. Okay, this notation allows corresponding many new classes of symbols. Okay, notation of the Fredholm apparatus. The apparatus A is called Fredholm if dim Kerr is finite, and dim co-kern also finite. The index of phi operators is the difference between dimension kernel or co-kernel. И central theorem of the Simonenko. Let function I is essentially bounding function. Toeplitz operator T with symbol I is phi operator in space LP plus for P between 1 and infinity. If and only if AIT admit P factorization. If IT admit P factorization, then index of the operator T at A equal minus kappa, and for kappa equal to 0, respectively positive and negative, the operator Ti is invertible, left invertible, or right invertible. For example, if we have kappa equal to 0, the operator T is invertible operator, and we have this nice formula. It would be noted that this formula very close to the last condition. To this condition, the condition B of the notation P factorization. Okay. Theorem 2 is consequence of theorem 1. If we have that operator symbol admit P factorization, it's possible to show that essential infimum of symbol more the zero, if we can consider the ray AP divided absolute value of AT, that is omega of T is unimodular function, the function take the values almost every year equal to zero. It's the function AT, the function absolute value AT with this condition is always admit P factorization with bounded factors. So we can reduce the problem for arbitrary symbol to the problem for the unimodular function, Okay. In this case, if symbol is unimodular function, we have more nice representation of the P factorization. This factorization depends of only one function, A or T, that belongs to the LP with plus. E, we have this condition, this operator HS 1 over H is bounding space LP. Condition 2 is equivalently of condition 3. S bounded is weight space LP, where weight coincides with absolute value of H. So we can see that the notation of phi factorization is connected with so-called weights Markenhaupt weight, in terms of which we will see we have the criterion of bounded of operator S in weight space, in weight space, in weight space. Okay, so if we have, with the help of notation phi factorization, we consider the cases of continuous function, piecewise continuous function. It's more or less classical result. But the problem is more delicate if we should like consider the symbol with the discontinuous of the second type, so-called the discontinued with a strongly oscillation near the discontinuous. For consider of this problem, it is possible consider the following construction. Omega is the unimodular function, so we can consider the superposition A of omega, and this function is functions with the discontinuous of the second type if omega has the discontinuous of the second type. For example, if we have A like the function with discontinuous of the with piecewise continuous, then A superposition omega is function that have infinite discontinuous of the unit circle. And arise the problem, natural problem, if A of t admits per factorization, then does function A superposition omega admit per factorization or no? So we have two problems. The first problem is construct of the sufficient condition for the function omega such that we have the per factorization of the superposition. And the problem, if A admits per factorization, then does function A superposition admit per factorization or no? So I have seen this problem in 1984. During the 14 years, I come back to this problem once more. No have no success because I have thought that the answer of this problem yes, but in really, like we have shown now with my co-author Albrecht Böttcher in 1998, the general answer is no. So more detail. Definition 3. Function, unimodular function that belong H infinity. H infinity is the set of all bounded inside of T analytic function. In this case, if we take any function, the problem about superposition of A and omega is more natural because why? Because the superposition in analytic function is analytic function and sorry, is analytic function. And we can prove that the condition I is true. And we must check the condition 2 or 3 only. I have mentioned that this problem has the strongly connection with so-called Mackenhout wedge, and we introduce this Mackenhout wedge. A measurable function, non-negative measurable function omega is called wedge if the set of zeros on points where weight take the value infinity has measure zero. And definition 2, if H omega is said to belong the Mackenhout class AP, if omega belong LP, 1 over omega belong LQ, if we have the following supremum is finite. Okay. And we have the following classical theorem of Hunt, Mackenhout, and Widen in 1973, that S is bounded operator on the weight Lebesgue space with the norm, with this norm, if in weight LP space, if and only if omega belong A of P, A of P. So it gives to us possibility to check the condition 2E in the definition of L factorization. So we must to consider the unimodular function A over absolute value A. If A admits LP factorization, so this function, this unimodular function, also admits LP factorization. It has the following representation: H conjugate over H. Okay. So we have in this case, H belongs HP, 1 over H belongs HQ, and absolute value H belongs the Mackenhout class of HP, as HP. So we must consider the A superposition U divided of the absolute value of this function, and we must prove that this ratio H superposition U conjugate over H superposition satisfy the condition A factorization. So according to the classical Littlewood theorem, we have that H superposition U belong HP, or 1 over H of this function belong HQ, and we must to check this condition. It's A superposition U does belong to HP or no. So I cannot to prove this, I cannot to resolve this problem almost 14 years. And because many examples of the function satisfied of this condition, namely absolute value h belong h superposition U belong AP. For example, for P equal to 2, this conjecture is true. For many classes of any function, also give to our examples if our conjugation is true convenient. For example, if you take this singular any function into, so the superposition is close to the periodic function, is true. There exist many so-called Blaschke products. It's white class of the 1 minute of the give to us the example if this condition is true. So the main theorem of this talk, if omega belong A2 with any function, then omega superposition U belong A2. If we have P does not equal 2, then we have let sigma be any numbers corresponding interval, then the function omega t equal t minus 1 in power minus sigma is await AP, but there is some any function, some Blaschke product, such that this superposition is not await in AP. So the answer of this conjugate is negative. It was proved in 1998. Thank you very much.